Hey guys, let's spend some quality time together and figure out the integrated rate law for a second order reaction. A second order reaction has the rate proportional to both a rate constant and the concentration of a reactant squared. Now to get the integrated rate law, we're going to have to write rate as a differential. What I mean by that is that rate is actually a measurement of the disappearance of A, that's our reactant, over time, and again, it's proportional to Ka squared. Now, in order to actually integrate this, I'm going to have to separate my variables. What I mean by that is I'm going to have to leave dA on the left and move my A squared to the right. Notice it moved from the top down into the denominator because I had to divide both sides by A squared. I'm going to move my negative to the other side, and I'm going to move my dt to the other side. It comes to the top because I had to undo division by dt on this side. Now I've got all my a's on one side and all my t's on the other. What we're going to do now is literally integrate this side and integrate this side. So here we go. Let me grab another piece of paper here. I'm going to rewrite this here, just so you guys really see what I'm about to do. I'm going to integrate 1 over a squared dA, and on this side, I'm going to integrate nothing, dt, or rather 1 dt, I should say. Negative and k are constants, so I'm allowed to put them out on the other side of the integral here. That's the integration rule. If you don't know integration rules, I'm not exactly sure why you're watching this, but don't worry, we're about to get to the juiciest bits. My favorite parts. Anyways, what's the integral of 1 over a squared? The answer to that is negative 1 over a. What's the integral of 1 dt? The answer is just t. Now what I really need here is to take this from time 0 to time t, and I need to take this from time 0 to time t. If you're familiar with integration, this is probably a notation you're familiar with. What it really means is negative 1 over a at time t minus negative 1 over a at time 0 is equal to, again, negative k t at time t minus t at time 0. Obviously, t is 0 at time 0. Now, this is technically a version of my integrated rate law, but it doesn't look very pretty. And as we all know, being pretty is what matters. So we've got to clean this up a bit. I'm going to multiply both sides by negative 1. That's going to help me cancel some of these negatives. 1 over at minus 1 over a naught is kt. And so what I end up with here is 1 over a of t is kt plus 1 over a naught. This is my actual great-looking integrated rate law. And the reason you should care about this is because this proves that if I graph 1 over at, or rather 1 over my concentration on my y-axis and t on my x-axis, I should end up with a straight line with a slope of k and a y-intercept of 1 over a naught. The whole point of doing an integrated rate law is to turn what is ostensibly just something that shows you how fast the reaction is going into a concentration versus time relationship. And again, let me emphasize, this proves that for a second order reaction, 1 over the concentration is linear over time. If you're given time concentration data and this kind of graph ends up being a line, that proves that it's second order. drop the mic. That's how it goes. Best of luck to you.